here's an interesting example. So once you study 2 dimensions and vectors in physics, you're going to be able to run into some of these problems where they force you into looking at multiple vectors and then things that are kind of shifting around. So here we have a boat, and it is crossing a lake. It's moving at a constant rate of 85 kilometers an hour north. So if you can see there, so let's say, so here's your little boat, right? So it is moving up. So this is 85 kilometers, and we'll assume that this is north. So this boat is moving along, and I guess the dock is exactly 1.5 kilometers away. So if it was going straight, here would have been your actual dock, okay, that you have. Now, there's a problem. Now, of course, when you are kind of driving, okay, or you're running a boat, you don't often think about the actual components of the wind, because your tires are able to resist that particular wind, okay, and then you can kind of move in a certain direction. So when you're dealing with a boat, okay, and there is a wind that you have, as they're saying in part number A, okay, this particular wind is 25 kilometers per hour east. So unless you purposely actually kind of steer in such a way that you're kind of going, okay, against, okay, the wind, and that is leading into kind of heading directions, okay, and then bearings and so on. So maybe I'll put up a link up above that, up above there. When you're dealing with those and you don't do anything, the wind is actually going to push you off course. So if you were just kind of heading through, the wind would have been pushing you off course. So here, as you're moving along, the wind would have been pushing you. So what you would have been doing is, instead of going in this direction, the wind would have been pushing you, and you would have been going off in a different type of direction. Now, when you do this, now, of course, we can draw this out for ourselves. So let's say if this is our actual boat moving, right? So this is 25 kilometers east. So we would have had a resultant vector, right? So we would have been pushed in that direction. Now, because we know what these are, so this is 85, this is 25, it's all in kilometers per hour. So we can find out what that actual resultant vector is, right? So it's going to have a velocity. So we can find the hypotenuse by simply doing the Pythagorean theorem. So if that's what you were asked, great. Here, what we're asked is, how long would it take for the boat to get to the other side? So here's the interesting thing. Now, if there was no wind and you're just moving at a constant rate, well, what you know is that your actual time that you would be running into, that your velocity, okay, that you have, so your velocity vector is nothing else but the actual displacement all over the change in time. Now, for us, we're given all of this information. So we know that this is 85, this equals, my displacement is 1.5 kilometers, and then here is my delta t. So I can solve for delta t in here, so that's not a problem. I can multiply delta t by both sides, or we're going to get 1.5 divided by 85, and it's going to give us the time. And that time would have been in hours. It's going to be a small amount. We can change it to minutes or seconds as much as we like, although they don't really ask us in here, so we can keep it in whatever units we prefer. So that is without the wind, and people understand that. But then they think, well, if I'm getting pushed away, isn't it going to take me longer? So the interesting thing is, no. Because of the fact that this wind is actually perpendicular to the direction of your movement, so it is at a 90 degree here, so it's exactly east, it doesn't have any impact on your actual motion in the y direction. It will have an impact on your motion in the x direction, assuming that this is your y direction and this is your x direction here. So it is going to push you off course here. But it doesn't mean that it's going to take you longer. You're still going to be continuously moving at 85, okay, as you're going, but you're going to get pushed off course. So that's what's going to happen. And now, in this case, once you have the actual time, so this time, whatever it might be, so if I take this in, let's see what this would be. 1.5 divided by 85, it's going to be rather small. So this would have been in hours, right? So that's the actual time that we would have in hours. So I'm going to just write it out for myself, and I'm going to keep, actually I'm going to write it in scientific notation, 1.7647, okay, let's say 10. I'm going to keep several decimal places to the -2, and this is in, in hours right there. And of course I can change this to minutes if I wanted to, so I can take that answer, multiply it by 60 minutes per hour, and this would have been about a minute. So it wouldn't have taken us too long, because 85 kilometers an hour in a boat is actually really fast. So that's what it would be, okay, in terms of, so let me take this out of here, okay, in terms of the amount of time that it would take. So this is a great question to be able to ask. Now, the other question that they ask us is, how far off its destination, okay, would the boat end up if it continued at the current rate? So here, if the dock is right there, well, you're going to get pushed over. So you're going to get pushed over to the side, okay, and you're going to be traveling along. So you're going to travel all the way through. So in the vertical, so in the north direction, we're going to travel 1.5 kilometers, but we're also going to get pushed off course here, right? So now that's what they're asking. So they're saying, how far off our destination would we be? So this is the x direction now. So, the displacement that we would have in here would have been equal to whatever your velocity is multiplied by the time. Okay, so this would have been just your actual velocity, okay, that you have. And this is the velocity in the x direction, right, or east, okay, because we're moving east, multiplied by the amount of time that this wind was actually acting on the boat. And that's the total time that it took to get to the other side. So here, what this would have been is, okay, so it would have been this right here. We would have had the time itself, and we also know what the actual velocity was, which was 25, kilometers per hour multiplied by, and this would have been times that tiny amount. Well, I have removed it, so I'm going to put it back in. So 25 times, this is 1.5 divided by 85, so I'll just keep it as it was. Okay, so whatever, once I substituted that in, we would have gotten 0.441, etc. I can round this. Again, there's no rounding in here, it doesn't state, although everything seems to be to two significant figures. So maybe that's what I should do. So this would have been 0.44 kilometers. That's how far off course we would have been. So it's 440 meters approximately that we would get pushed off course. Okay, so that's how you would have been tackling this situation that you would have had. So those are the two kind of questions related here. Now I'm going to give you one more example here, okay? And this example it's exactly the same, but it's telling us that now the wind is 25 kilometers an hour, but it's not just east. It's 45 degrees south of east, right? So what would this mean? Well, okay, so what this would mean is, okay, we're moving along here, so that's all great. This is 85 kilometers per hour. But then we have, okay, this wind, and now this particular wind, okay, as we're going through, is at an angle. Now this angle, okay, so notice if this is east, okay, so this angle is 45 degrees, right? So it's east 45 degrees south, so we're going down. So now all of a sudden, and this is now 25 kilometers, right, in here. So this is now interesting, because what does this actually tell us? This tells us that now the wind does have a component against our actual speed of the boat. So as our boat is moving along and it's going north, right, the wind, okay, that 45 degrees, that particular wind is going to have two components. So if I'm going to take this out, okay, right here, it's going to have two components. It's going to have a component which is going to still push us, right? So this is going to be the wind's, okay, component in the x direction. Maybe I'll put W for wind. And it's going to have a direction, okay, in the y component. And notice this y component is going to be against our actual movement of the boat. So this is going to be the y component that we would have, okay, of the wind. And this one is 25 kilometers per hour. Now we know what this angle is, right? Okay, so, well, we also, I guess, know what this angle is because that would have been 90 degrees in total in there. So we can find out what those components are. Okay, so those components, not that we need, because here it just asks us how long would it take. So really, we just kind of want to be able to know what the y component is. And so for that, the actual y component, although I'll do the x component as well, just to remind you, and this is breaking down a vector into its component. I'll put up a link up above there if you want to see a little bit more. So any of these, this is going to be 25 kilometers per hour multiplied by, and notice this is going to be the cos of the angle, which is cos of 45, which I guess is 1 over square root of 2. And then your y component, okay, of the wind is also 25, but this is going to be sine of 45, although sine of 45 and cos of 45 are identical. So we know exactly what these are. Now that we have these two components, well, one of the components, so the component which is in the x, this does not have an impact on the boat, but this component certainly does have an impact on our boat, because now our boat is moving in this direction and there is a component in the wind which is pushing it back. So now what is, okay, that full component? So, the actual velocity of the boat, okay, that we would have is going to be now the 85, and then this is the total velocity, minus whatever the actual, so this is going to be 25, sine of 45 degrees. Okay, and then we can find out exactly what this is. So we're going to be subtracting that small little piece right there. So it's going to get subtracted off. So 85 minus, and this is going to be 25 multiplied by the sine. Okay, so sine of 45. And, you can plug that in, or if you remember your unit circle, okay, so that would have been giving you, so this is 67.3. I'll just keep these, okay, for the moment. Okay, this is kilometers per hour. Okay, so I'm not going to round it, it's an intermediate step. It's asking us for time, so that is no different, so this will just come. Okay, so sorry, this is for the velocity, which is the change, okay, so this is the displacement, okay, that we have, and then this is your delta t. Well, this is still 1.5 kilometers, but now we're going slower. So my delta t, so if you multiply both sides, by delta t as we did in the first one, right there, okay, and then we're going to divide by the v, okay, on both sides. So what we're going to get is 1.5 kilometers divided by, and this is going to be divided by the 67.3, 2, etc., okay, depending how many decimal places you want to keep there. So that's what we would get. So 1.5 divided by 67.32233, and this is going to give us the time. So it's going to take us a longer now. Okay, so notice it's a very short time. Maybe what I'll do is multiply it by 60. Okay, so this is going to be 1.34 approximately, or rounded to 2, okay, minutes. So 1.3 minutes. So about 1 minute and 20 seconds, I guess, give or take. So that's what it would have been. It would have taken us a little bit longer. And the key thing is that now, you had to break this down into its x and y components, because one of its components was actually opposing the boat. Now, if the wind was in your favor, okay, then, you could have been adding and you would have actually gotten there faster because the wind was also pushing you along. So that would have been nice, but not in this case, okay? It was opposing you. All right, so this is an example which now takes vectors and it gives you a little bit of an application. I know that it's a common application in physics you'll run into, most likely in grade 11 or possibly an introductory physics class, just to force you to see if you understand how to break down vectors and then how to apply it to something which is going at a constant speed, okay, or constant velocity in this case. All right, so thanks for watching, and we'll see you in a future video. Bye, everybody.